All right, welcome. Like I said, we're talking about the modulating gas furnaces, the 987M Bryant Evolution and the 59MN7 Carrier furnace. So just a quick snapshot here, just to get us all on the same page. This shows the energy usage breakdown for the entire United States as a national average for residential usage. And you can see here about 44% of the energy usage in the average United States home is related to space heating. So obviously having an efficient furnace can make a pretty good impact on that. There's obviously other things that contribute to the efficiency of your house's heating system, like the insulation you have in your walls and air leakage and all that stuff, but the furnace can play a pretty good portion of that. So we're going to talk about that today. So here's the Bryant current condensing furnace lineup, and I'll show you the Carrier one in a second. And we're not going to really talk about 80% furnaces. They're kind of on their way of being phased out anyway. But today we're just talking about condensing furnaces. So there's actually 6 furnaces in the Bryant condensing furnace line, 5 of which we stock here in the Chicagoland area. Ignore that availability thing on the bottom. That was for last year, so all of these are available today. So kind of starting at the bottom here, working our way up. There are 2 furnaces in the Legacy line. And the way the model numbers work, anything that starts with a 9 in the Bryant model numbers means that it's 90% efficient. And that third digit is how efficient it is. So 912 is 92% efficient. The 1 means that it is a legacy line. So 9 means condensing, 1 means legacy line, 2 means 92% efficient, S means single stage. So that unit's a 92% AFUE furnace. The smallest size is 40,000 BTUs. The largest is 120. It is a single stage heating unit. It uses a PSC blower, which is a regular, just everyday fan blower. It's technically a 4-speed motor, and we are using 2 of the speed taps actively, 1 for heating, 1 for cooling. His big brother is the 915S. Basically, it's the same furnace, single stage PSC motor, but it's 95% AFUE instead of 92. Additionally, there also is one larger size that goes up to 140,000 BTUs because this entry-level style unit is used fairly frequently for commercial applications for larger areas. In the preferred series, which is the middle tier, there are actually 2 furnaces. However, one of them we do not stock here locally. We only stock the 925T. So 925, the 9 and 5 mean it's 95% efficient or higher. Some models actually hit 96%. 95 is the worst one in the line. The 2 means that it's the preferred series, so the middle tier, and the T means 2-stage. These also happen to have an ECM motor in them. It is not a variable speed ECM, it is a multi-speed ECM. So it happens to be a 5-speed motor, and we are actively using 3 of the speed taps. 1 for 2-stage cooling, 1 for 2-stage heating, and then the 3rd speed tap is used for 1-stage heating, 1-stage cooling, and continuous fan mode. There is a single stage unit in that line. We don't stock it here locally though. That's the 925S. Then we have the 2 Evolution units, which are the 986T and the 987M. The 8 signifies that it's the Evolution tier. The 96 means it's 96% efficient or better. The 987 means it's 97% efficient or better. The T means 2-stage. The M means modulating gas. These are both variable speed units. So that means the fan speed can ramp up and down based on the cooling demand, static pressure resistance in the duct, things like that. So one is modulating and one is modulating gas with variable speed fan. The other one is 2-stage gas with variable speed fan. The Carrier side, it's a very similar scenario. There are actually 7 furnaces in the lineup. We are only stocking 5. It is the same 5 we stock on the Bryant side of the equation. So at the entry level, it's the Comfort series. You got your PSC fan motor with single stage, 92% AFUE. Your PSC fan motor with single stage, 95% AFUE. Then in the Performance series, we just stocked the 1 multi-speed ECM with 2-stage gas, 95 and 96% AFUE depending on the exact size of the unit. Then the 2 Infinity series units, which are both variable speed motors, fully variable speed, 2-stage gas, 96% AFUE, modulating gas, 97 and sometimes 98% AFUE depending on the model. So hopefully that kind of makes sense. We're going to focus much of our discussion on the 59MN7 and for the Bryant 987M. I just want to give you kind of idea of the whole lineup there. Many of the features apply to all the units in the line, so I'll try to distinguish what I'm talking about. Does this apply to everything, or does this only apply to the modulating gas unit? So for starters, obviously the modulating gas only applies to the two modulating gas units, the one Carrier and the one Bryant. It modulates in 1% increments from a minimum of 40% gas fire up to 100%. So that's basically 61 stages of capacity. So it can operate at 40%, 52, 97, 100, and anywhere in between any of those. These units are 35 inches in height, which compared to our previous condensing furnaces that we had last year and prior, those were 40 inches. So these are a full 5 inches shorter. The reason to get shorter, main reason is so you can fit more stuff in the duct, in the supply duct. People are always trying to add humidifiers and larger evaporator coils for better efficiency and UV lights and air purifiers and all these different things in the supply duct. So having a shorter furnace means a little bit more room in the house to add some more stuff to the supply duct. So that does help out with that. Because we did switch to 35-inch furnace height, we did have to change the heat exchanger style. And I'll show you the heat exchangers in a little bit, but we had to make them more compact. All the units in the entire lineup are 35 inches, all single stage, two stage, and modulating, and they are all four-way multi-poise. That means every single model can be upflow, every single model can be downflow, or every single model can be horizontal left or horizontal right. Every single one of them can be rotated. There's no dedicated model numbers in the Carrier and Bryant lineups at all when it comes to condensing furnaces. They all have built-in internal condensate traps. I'll show you some zoom ups of that. And the venting flexibility is pretty large. We can go some pretty long runs on these guys, and we'll talk about that as well. In terms of accessing these guys, it is now a two-piece design, two-door design, top door, bottom door. The bottom door accesses your blower, circuit boards, thermostat wiring, and things like that. The top half has your combustion chamber, your pressure switches, and all that stuff, inducer motor, etc. There's no longer any nut driver or screwdrivers needed to access anything. You just got the two quarter turn knobs on either the top or the bottom door. You turn those and pull the door off. You're into everything. There's no separated combustion compartment for the burner section. The whole top half of the unit is the separated combustion. So the doors are gasketed. All your penetrations are gasketed. So the good news is you can get right in there and service anything without having to have a nut driver to take any panels off. So the igniter is a little bit easier to get at. The blower does slide out on rails. I'll show you some of that stuff. It is a fairly service-friendly type unit. And there's the guts of those guys there. We'll go into each piece individually. So we'll talk about heat exchangers, inducer motors, venting, fan access, etc. All right, so anytime we have a fully modulating gas valve, we also have a fully variable speed fan motor, two-way communicating between the furnace and the motor itself. And we also have a variable speed inducer motor attached to that unit. So generally speaking, if we got a one-stage gas, we got a one-stage inducer motor with basically a one-stage blower fan. If we got two-stage gas, we basically have a two-stage inducer with a two-stage blower. And if we got fully modulating gas, we got variable speed blower and variable speed inducer. So those things kind of all line up. The more capacity stages of gas I have, the more inducer and blower speeds that I have. In terms of the heat exchangers on these units, the primary heat exchanger is aluminized steel, and then the secondary heat exchanger is stainless steel. Obviously, secondary heat exchangers, because of the corrosive nature of the condensate, have the ability to deteriorate, so we like to make those out of stainless steel to obviously improve their life. On these modulating gas units, when we say in the model number that's a 59MN7, I told you the 7 means 97%. And the same thing on the Bryant, 987M, the 7 means 97%. That's the worst efficiency of anything in that series. There are some of them that are even higher, such as the 60,000 BTU size of the Carrier one here is shown as 98.5%. So it's in the 97% tier, but some of the models do break 98%. So you can rest assured when you're going for utility rebates and stuff like that that are triggered on 97%, you got no problem getting there with any of these style units. All right, I mentioned the height being lower, but there are also more width choices than we used to have a year ago and prior. We now have a 14-inch wide cabinet. This comes into play in some of these condo retrofits and things like that. Obviously, there's other concerns in the counter retrofit, like how you're going to vent it, but at least now you can get a furnace that's skinny enough to actually fit in the existing closet. So they come in 14, 17, 21, and 24-inch wide cabinets now. Obviously, every single BTU size is not available in every width. I can't shove 120,000 BTUs to the 14-inch cabinet and so forth. I'll show you all the details on the venting and condensate. I'll show you pictures of it and kind of explain those as we go through these guys here. So let's start with the individual pieces of the furnace. And by the way, we're going to go through all these different pieces, and then we're going to talk a little bit more about the modulating sequence and how to explain it to homeowners and things like that. But first, let's discuss all the pieces. So here's our heat exchanger. There's two separate heat exchangers, the primary and the secondary. The primary is on top. So in this case, it's a 4-cell burner. So I have 4 different cells. I might have 3, I might have 5, whatever it's going to be, but this one happens to be 4. So I got flame going into each one of these top 4 here. They pass through this heat exchanger, come back around, make a 180, come back around, make another 180, and then make another 180 at the back end to go into the secondary heat exchanger. So this bottom half here, and hopefully you guys can all see my mouse, this bottom half here is the secondary heat exchanger. So the top half is this clamshell type design. The secondary is the fin and tube type design. So I got all these individual tubes going through here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 30 tubes going through here, and then they have fins on them to spread out the heat, obviously. So each one of these guys is attached to the fin. The fin spreads out the heat. Additionally, inside of each of these tubes, I'm not sure how well you can see it, but you see those little metal tabs sticking out of each tube? If you were to pull those metal tabs out, you'd have a corkscrewed piece of sheet metal, and his job is to be inside that heat exchanger, causing turbulence. The more turbulence I have with the gas flowing through there, the more likely it is an individual gas molecule will touch the exterior side of the tube wall, which will help it transfer heat. So I want a little bit of turbulence in there so I don't have laminar flow, so I can get more heat transfer. So this style heat exchanger, compared to our previous designs, does help it get a little bit shorter. The fin and tube does not take up as much vertical space as our old heat exchanger designs did. So I can get, that's where you get some of that 5 inches of vertical height savings. And then to squeak more efficiency out of there, that's why they got these turbulators in there, to get another couple tenths of a % out here so we can get these things up into the high 90s in terms of efficiency. All right, in terms of installing these guys, it's extremely flexible. You can pretty much install them to replace just about any other piece of equipment. By that I mean the gas connection can either be on the left-hand or the right-hand side of the unit, the electrical left or right-hand side, the condensate left or right, the combustion air inlet left, right, or top, the venting exhaust left, right, or top, the return air left, right, or bottom. So I got pretty good flexibility on whatever way they had the old unit connected, electric on the left, condensate on the right, whatever it was. I can pretty much put this in its spot and not have to change those services and move gas piping, condensate piping, or electrical conduit. Right, so here's showing you some examples of that. Depending on where I chose to put the various penetrations, I'll have different types of attachments I can use to seal these up. So if you remember, the top half of this unit is the combustion chamber. So if I jam a combustion pipe or an exhaust pipe or a gas line or something into the side of this unit, I don't want air leaking around that pipe because that's part of my combustion chamber. So I want this to be a sealed combustion chamber, or maybe we'll call it a semi-sealed because it's not perfectly sealed. But in the loose parts bag, they're going to ship to you the various grommets that you would put on the gas pipes and the termination connectors for the vent pipes with little gasket seals to keep that air from infiltrating to there, so all the combustion air has to get sucked from the outside air combustion pipe. Here is our heat exchanger assembly. So this is our inducer motor here. My pressure switch is over on the left-hand side, my condensate in the bottom right-hand corner of the picture, and my exhaust venting elbow on the top half. There is no piping connection for the combustion air because if you recall, all the combustion air is just going to come into the top half of the cabinet and the piping then stops. So the whole top half is the combustion air. This venting elbow rotates. It can rotate any direction depending on which way I need to vent it out. So I can vent vertical, I can vent horizontal left, I can vent horizontal right. There's basically, for lack of a better description, a radiator hose clamp that I would adjust and open up, rotate the elbow, and then lock it down. So it's very easy to go out left, right, or top and switch those guys. If I were to flip this unit on its side, or if I was to install it in a downflow configuration, for example, I would need to rotate the venting elbow. I'm also going to have to relocate the condensate trap. Right now I'm set up for upflow, which means the air is coming in the bottom where my mouse is, moving to the top, the heat exchanger, and exhausting out the top, or supplying out the top, I should say. If I were to flip this whole thing upside down and make this unit a downflow unit, now this condensate trap isn't going to be in the bottom right-hand corner of the screen. It's going to be in the upper left. Well, water's not going to do a very good job of flowing up. So what I got to do is, if you see over here, these collector box plugs, I take those 3 plugs out. I take out a couple screws on the condensate trap over here. I move the condensate trap to the top. I move the plugs down to the bottom right. And now everything's in the correct spot when I flip it over. So here's a zoom up of that condensate trap. In this particular example, this is a demo piece. It's showing it as clear. In the ones you actually get in the units, the front half of this is white. It's solid white. And the back half is clear. The reason it's like that is we wanted to make them clear so as a technician you can look at this thing and determine if something's plugging up the condensate trap. But homeowners don't like to see gunk stuck in there. And gunk's a technical term, by the way. So we made the front half of it white. So if a homeowner looks inside their furnace, all they're going to see is the white plate. They're not going to see anything behind it. But you as a technician, if you're troubleshooting, you can take it off, flip it around, look at the back, and see, oh yeah, there is something stuck in there. In terms of the venting, so this is upflow configuration. So my supply air, my return air, excuse me, is coming from the side or the bottom in this case, and all my supply air is going out the top of these units. I have choice on where I'm going to do my venting. So I can vent all on the left side like they're showing here. The blue line is my combustion air coming in. It terminates at the housing of the unit, and then all my combustion air would fill this chamber, and my inducer fan would suck it from there. The exhaust air comes out this elbow and goes out the left side in this example. So I would have had to rotate the elbow 90 degrees counterclockwise and then lock it back down so I could vent out the left. If I didn't want to if I didn't need to change it at all, it's already set up to go vertically up, or I could have rotated it 90 degrees right and went out the side of the cabinet. So all I got to do is rotate that elbow and I can vent left, vertical, or right. If I was to put this unit in a downflow configuration, meaning that I had flipped the entire unit upside down, so my return air is coming in what is now the top, and my supply air is going out the bottom into the ground, I could do it that way. Obviously, I can't vent straight down. That's not going to work. But I could rotate the elbow this way, so I'm venting out the left. I could rotate it this way, so I'm venting out the right. Or I can rotate it 180 degrees, cut back through the blower housing, and vent out what is now the top of the unit. If I'm going to cut through the blower housing, there's 2 caveats. One is I got to get this internal vent kit that's mentioned down here at the bottom, which is basically the seals and gasketing to seal up these penetrations I'm now making in the blower housing. The other thing I got to think about is now I'm putting these 2 PVC pipes right in front of my blower motor and circuit boards, which is going to make troubleshooting down the road obviously harder if I got to remove PVC pipe to get to the furnace motor and to the furnace circuit board. So venting this way is to be avoided. It's more service work, and it requires you to buy extra piece for this venting kit. However, if you're in a tight, skinny closet, this may be your only choice, and this unit does allow you to do it. But normally you're going to go left or go right. Similar scenario for horizontal. I'm just checking to see if we have any questions here, and we don't yet. Similar scenario for horizontal. If I'm going to supply horizontal left or horizontal right, which is the next screen. Oh, I skipped that screen actually. It'd be a similar type scenario. This venting elbow is already pointing this way, so this is the default configuration. The venting exhaust will go to the left and then out of the building. I could also rotate it 90 degrees and have it go out what used to be the side of the unit and now is the top. Or I can rotate it 180, cut back to the blower housing, and the exhaust out that way. Once again, I need an internal vent kit if I want to cut through the blower housing, and I am blocking off access to my unit. You'll also notice that the condensate trap, when you put this thing in horizontal orientation, has to be rotated. So not only does it have to flip from the bottom right to the top left, it also has to be rotated so gravity works in its favor. And it does cause it to stick about an inch, inch and a half out of the housing of the unit, which is not a big deal because they ship you the grommet with that to seal up that penetration. However, if you're planning on laying this furnace on the ground, that's not going to work. It's going to have to be up on little blocks or something like that, or hanging below a ceiling or something. This is a zoom up of that venting elbow. There's actually 2 clamps on there which look like radiator hose clamps. The first one here on the back is for adjusting which way the elbow orientates. You can loosen that clamp, Then use your hand to rotate this elbow 90 or 180 or 270 degrees, and then lock that clamp back down. The other clamp on top here is for the PVC pipe to connect to. In terms of our vent sizing, this style unit can vent significantly further than any previous Bryant Care units that we've ever had for condensing furnaces. So to give you some examples of that, here's one of the venting tables out of one of the units. I believe this came out of a 59 TN6. The venting tables are identical for all of the furnaces except the modulating gas furnaces. They actually have a little bit higher numbers than this. They can vent slightly farther than the rest of the furnaces because their inducer motor has the ability to overspeed a little bit. But if you look at this table here, this is a pretty safe assumption, and this covers every furnace. In some cases, you can go a little bit further. We really only got to look at the top half of the chart. I didn't even bother printing all the bottom ones because we only need the first one, which is less than 2,000 feet of altitude for Chicago. We're like 600 feet, so this is where we're at. I picked the size of my furnace, so in this case, let's pretend I have a 100,000 BTU furnace. So it says I cannot vent this in 1.5-inch pipe. I could vent it in 2-inch pipe up to 25 feet. I could do 2.5 up to 110, but 2.5 is kind of a bit of an oddball size. I can go in 3-inch pipe up to 235 and 4-inch pipe up to 265. This feet, say, for example, let's say I do 3-inch pipe, 235 feet. That is the length of pipe, including the equivalent length of any elbows and things like that. So every fitting is going to have a certain equivalent pipe penalty associated with it. I have to add those in. So here gives you some examples of that. On the 3-inch one, if I got a long radius elbow, I got basically a 3-foot penalty for each one of those elbows that I put in. They're telling me with 3-inch pipe I can't even do any of the small elbows. There's too much of a pressure drop. Right? But if I was looking at the 2-inch pipe, a long radius is a 3-foot penalty. Some of the tighter ones are going to be 5- and 8-foot penalties. Right? So depending on whether it's 80 or 90 or 45 and whether it's tight or long radius will determine how much penalty I'm going to have associated with that guy. So I got to add up all those plus my length of pipe and make sure it's under these limits. These are pretty substantial limits, so you shouldn't have any problem, even venting up multiple story buildings this way. Now, obviously, you got to find someone to run the pipe. That could be a problem in a multi-story condo building, but the furnace can handle it. You are allowed to do 2 pipe, as you see here, or 1 pipe installations. The length is the exact same either way. These are the maximums for either scenario. 1 pipe installation means I have an exhaust pipe, but I have no combustion intake pipe from the outdoors. This furnace could be installed either way. If you are going to install it without the combustion intake pipe, first of all, we recommend that you have 2 pipes, 1 for combustion from the outdoors, 1 for exhaust. Because if you don't take the combustion from outdoors, you're stealing it from the space, which can cause draft issues in terms of comfort, or it could actually cause other appliances to perhaps inadvertently backdraft, like a water heater or a fireplace or something like that. So we do recommend a 2-pipe installation. If you want to install it with 1 pipe, you can. The furnace can handle that. You're responsible for making sure none of your other appliances backdraft. But you also have to do a little bit of piping on the combustion inlet. Basically, they're making you put a 12-inch pipe and an elbow on there. And they don't care if it's 12 inches then the elbow or the elbow then 12 inches. It doesn't matter. We're basically just trying to get a little bit of restriction on that inducer motor so we can generate some static. So we just need a little bit of restriction, not much, to make sure we're not just pulling on nothing. If you guys have any questions, type them in that question chat box, and I'll do my best to address them. We actually kind of already talked about the heat exchanger, but here's a slightly better zoomed up picture. You can see a little bit better what those fins look like, and then more importantly, what those little turbulators look like. And you could pull those out and clean the tubes if you need to, years down the road. So the gas valve itself is nothing overly sexy. It's basically a gas valve. It just so happens that we can control the capacity of the gas valve and modulate it. So like I said, the minimum is 40% of firing. The maximum is 100%, and we can pick anywhere in between there. There is an adjustment screw on the bottom right-hand side you can see there. And that's for setting up this gas valve. Typically, when you're setting this up, you're setting the low and the high firing rate. Other manufacturers of modulating gas valves have you set a middle position, and then you got to go check it at low and check it at high to make sure that everything's still okay. This one's a little bit different. You set it at low and you set it at high, and then it figures out its little, little curve in between there. It is a diaphragm type valve, so it is fairly slow operating, which is good. We don't want it to be too fast. And it does have 61 steps of control that we can handle here, 40 to 100%. We'll go back to that gas valve sequence a little bit here. The last real kind of piece here is the motor itself. This is what that guy looks like. It does slide out, so you can remove a couple screws from the top half here, and this whole motor can slide out on that chassis there. And they do give you enough electrical wiring whip here that I don't even have to disconnect anything. And if you're smart, you give yourself a little bit extra thermostat connection wire, and you won't have to disconnect anything at all, and you could turn power off, slide this motor out, set it on the ground next to the furnace, and then either change out the motor or access the heat exchanger from underneath without ever having to take the wires off. Obviously, every time you take wires off, you got to remember where you put them, and that tends to be problematic. So if you never have to take them off, you don't ever have to worry about that. Charles has typed in a question, at ignition, does it start at full capacity, half, etc.? So when this thing first fires up, what it's going to do is start at a middle capacity, approximately 75%. And then after it gets good, clean combustion, it's going to immediately modulate down, assuming you didn't want very much heat, it's going to immediately modulate down to 40% and hover down there. And then it can ramp from 40 to 100% up and down. Other modulating gas valves and other manufacturers' furnaces tend to only modulate upward, and they don't have the ability to modulate back downward. They don't have algorithms to do that. So they keep modulating upward as you need more and more heat, and then eventually the furnace would stage off, and then it would wait a cycle, and then it would stage on again and try to predict where to start based on its previous starting history and how much capacity it needed. Ours does not work that way. Ours tends to not shut off ever. It modulates up, and then if it's too much capacity, it'll modulate back down. But when you do first fire it up, it will start at a medium capacity, approximately 70% of firing rate, and then modulate down towards 40% or whatever it needs to handle the BTUs that it needs. All right, so that's some of the pieces on there. What I want to talk about now is some of the benefits and some of the operation of how a modulating gas furnace works. And I'm going to do it from the perspective of talking to an end user because that is who you're going to have to convince that this is a good idea or a bad idea. So I'll kind of explain that from both a comfort standpoint, from an energy standpoint, and anything else you guys want to talk about. So first, just to give you a little bit of a snapshot of some of the areas that we work in here and how much heating is actually required in these areas. So I'm going to use Chicago as our example because most of you guys that logged in are from Chicago and associated suburbs. There are, well, first off, there are 8,760 hours in the year. What we're trying to do is look at hours that relate to the heating mode. We've defined heating mode to be anything below 65 degrees outside. Some people it's 60, some people it's 70, whatever. We're just talking about it in generality here. So below 65 degrees outside. Of the days when it's below 65, there's 6,000 hours in Chicago that we would have in that scenario. So 6,000 hours below 65, that means 2,760 hours above 65. So it is definitively a heating-dominated climate. And typically we're designing for -3, -4, -5 degrees outdoor air temperature in the Chicago area. I know some of you guys do -10. The new energy codes don't allow your load calcs to use -10, but if you want to think about for this discussion, that's fine too. But what I want to do right now is look at the hours where it's between 30 and 60. So above 30 but below 65. I got 4,500. That's more than half of my hours of the entire year, and 76% of all my heating hours are between 30 and 65 degrees. So yeah, I have to size your furnace for -5 or 0 degrees or whatever it is. I got to size it for that so it can handle that day, but the chance of it operating at full 100% capacity is almost nothing. It's going to spend very, very few hours below even 30 degrees, let alone 0 degrees. If you want to take it a step further and look at between 20 and 65, that's 5,400 of the 6,000. That means there's only 600 total hours below 20 degrees outside. And even at 20, I do not need full capacity heating. If I designed it for 0 or -5, I still got another 20, 25 degrees to go. So 90% of my hours are above 20 degrees. And if you look at the hours that are actually below 0, it ends up being less than 1%. It's a very, very small amount. But I got to size your furnace for that, so you got the capacity on those days. but I don't want to run your furnace at that unless it's really 0 degrees outside. Looking at it graphically, each one of these bars represents a 5-degree outdoor air temperature range. So on the bottom here, it goes from -23 to 97 on this chart, and this is 0 to 800 hours up the left-hand side. So if I look at, say, the 32-degree range, so the 5 degrees around 32, I got 650 hours there, another 600 hours at the 37 range, another 500 at 42. So all these tall bars here are in that middle range from 20 degrees to 65 degrees. I got very few bars down here below 20, very few run hours. Right? If I look at the ones below 0, it's basically like 200 hours total below 0 degrees. Cooling, you can see, is in blue. There's very few hours in cooling to begin with, and certainly very few above 90 degrees. It ends up being like 20, 25, 30 hours on average above 90 degrees. But the main part here I want you to think about is the heating is mainly in the quote-unquote mild time. 20 to 65 degrees is most of my heating demand. So the way we used to explain this kind of thing with the two-stage furnaces are that we used to talk about the little furnace, big furnace. And some of you may have done that selling example with end users before. Yeah, when it's -5 degrees, I got to give you this furnace that does 100,000 BTUs because that's how much heat your house loses. But man, it really kind of stinks that you got this big giant furnace that has to run all the time when it's almost never really 0 degrees outside. It'd be great if I could give you a little furnace that runs most of the time of the year, but then you still got this big furnace sitting next to it that handles the really cold days. But no one's going to buy 2 furnaces, so that doesn't make sense. But I think I can give you a furnace with 2 stages, a low fire and a high fire. It's kind of like having 2 furnaces in one box. One for when it's really cold, one for all the other days of the year. Well, the modulation example is kind of like that also. The difference there is that, well, it's not only 2 temperatures outside. It's not only 60 degrees outside or 0. It could be anywhere in between. So I don't need a little furnace and a big furnace. I need lots of furnaces. I need one for when it's 5 degrees outside, one for 10, one for 15, for 20. So a modulation kind of gives me that benefit. It gives me basically 61 little furnaces all inside one box. And I can operate whichever furnace I need to get whatever capacity I need based on how cold it is outside. Right? So that's kind of the way to kind of think about that. Another way you might explain it to someone is that if you want to boil a pot of water on your stove, right? You got the burner, you turn the burner on, and you let that water heat up to when it's boiling. But you don't want it to boil over the sides of the pot, so you got to turn the burner down, right? Well, you don't turn it all the way off, and then the water gets cold and you turn it back on, and then off, and then back on to boil the water, right? That doesn't make any sense. But that's kind of how you heat your house normally. You got a 1-stage furnace. You turn the burner on, it gets hot in the house, you turn it off. You turn it on, you turn it off. Or rather, the thermostat's doing it for you. Burner on, burner off. Burner on, burner off. Whereas with the pot of water boiling, you don't turn it on and off. You modulate the gas valve with your hand to get to the desired heating capacity that you need to boil the water, but not boil it off the side of the pot and not let it stop boiling either. Same thing with your furnace. I want the furnace capacity to modulate, although instead of my hand doing it, the thermostat's going to do it. It's going to modulate the gas valve for me to get me the correct amount of heating that I need for my house based on how fast heating is being lost at my house. There's probably 50 other analogies you can make for people to kind of try to explain this to them. This chart here shows you a typical heating load at someone's house. So on the bottom here we have -10 to 80 degrees. On the left-hand side we have 0 to 65,000 BTUs. So this guy's particular house was sized for 65,000 BTUs on a -10 degree day. That's that little dot over here on the top left. If I also did a load calculation for his house on a warmer day, say 55, 60 degrees, or I can even plot and figure out when he doesn't even need any heat. So in this case, at 57 degrees, this guy doesn't need any more heat in his house. He's got enough internal heat, he doesn't need anything. If I can do the load calculation there and do it at -10, or actually any 2 points, I could draw a straight line between those points, and that represents the load line for my house. So if I plotted those 2 points and then I looked at 30 degrees outside, at 30 degrees outside, this guy's house needs 27,000 BTUs. When it's 10 degrees outside, he needs 45,000 BTUs, right? So if I do 2 load calculations, I can then plot a line to represent this guy's entire home, or gal, whoever lives there, or both. So my goal is I want to give you the exact amount of BTUs to burn with your furnace to match whatever your house needs. How fast is your house losing heat? It's losing it at 37,000 BTUs an hour? Well, then I want to burn 37,000 BTUs an hour. I want to make it even. I want to give you exactly what you're asking for. And that's what the modulating gas valve's job is to do. It tracks this line up and down, up and down, up and down as it gets colder outside. Now, a couple things with that. One is that this furnace, in many cases, is not going to shut off. It's going to run continuously all winter long. There's only 3 times that the furnace should be shutting off. One is if it keeps getting warmer and warmer and warmer outside, I move down the line, and eventually I get less than 40%, which is my minimum gas valve. So less than 40%. What is this one? 6,500. So if I look at my calculator real quick, 65,000 times 0.4. So when I get down to 26,000 BTUs, so let's call it right here, that's as low as I can modulate down. So basically 35 degrees in this case. I might have to actually stage this guy on or off, depending on how big the furnace is. So if I put an oversized furnace in, it's going to stage on and off a lot. If I put a correctly sized furnace in, he's going to be able to modulate most of the year, and he's only going to have to shut off when I get down to some fairly warm temperature outside, 40 degrees, 45, 50, something like that. But even then, when he stages on and off, he goes from 0 to 40, 0 to 40, not 0 to 100, 0 to 100. So one time that he might shut off his burner is if it gets mild enough outside that he can't modulate down any farther at all. The other time he might actually have to shut off is if you walk up to the stat and change the set point. You were asking for 72 degrees. Now you walked up to it and bumped it down to 68. Well, it's going to look at it and calculate and then say, well, I'm actually 4 degrees hotter than you want, so I better start modulating down. Then he's going to modulate down to 40% and say, dang, I'm still way hotter than you wanted. I'm going to have to shut off for a while and let that thing drift down to 68 degrees in the house, then turn it back on and modulate from there. And the third time that he's going to shut off is going to be whenever you go into night setback, because it's the same thing as changing your set point, basically. The thermostat automatically switched us from 72 to, say, 65 degrees. The stat told the valve to ramp down as far as it could. It couldn't ramp down any further, so it basically said, well, I better stage off for a while and let the temperature in the house drift down to 65, and then I can go ahead and re-enable myself after that. So when it's fairly mild outside, when I change the set point manually, or when I go into nighttime setback or any time of unoccupied setback, those are the times the gas valve actually could shut off. Now, one of the things that a lot of people say, especially end users, when you're explaining this to them, I'm explaining to them saying how great this is going to be. It's never going to shut off. It's going to give you nice, consistent discharge air temperature. It's going to help with these hot spot, cold spots in your house, kind of like when you start talking to people about running their variable speed fan all the time. It helps with those hot and cold spots. Well, now it's like variable speed fan, but instead of dumping 70 degrees, then 120 into the duct, 70, 120, 70, 120 as the burner stages on and off, now you're putting in a nice, consistent 100, 105, 110, whatever it is. So they're going to get much better comfort. But you're telling them this thing's going to run all the time. So in their head, they're thinking, oh, crap, this is going to cost me a lot of money. It's never going to shut off. In reality, it actually costs you less money to operate the gas, which is why the modulating gas furnaces are 97, 98% efficient, because they're actually using less gas. But instead of getting all the gas blasted at one time, you're getting it trickling through the gas valve. So you're getting smaller amounts throughout the hour instead of big blasts a couple times in the hour. And one of the best ways I found to explain that to people is the garden watering example. So if you got a garden that requires, say, 5 gallons of water a day, I could go out there, stand in the yard with my hose, squirt 5 gallons of water on top of the garden and let it puddle up and then walk away. And there's this 5 gallons. Or I could buy one of those soaker hoses, lay it through the middle of my garden, turn on the water, let the soaker hose, let the water sprinkle out through there at a slower rate, and let that do that for 5 gallons, then shut it off. Which one uses more water? Obviously, it's a trick question. They both use 5 gallons of water. I just told you that, right? They both use 5 gallons of water, but do you want it to all puddle up on top of your garden in one big blast over the course of a minute? Or would you like it to trickle out over your garden for the entire hour, right? Which one's better for the garden, the big giant puddle or the slow soaker hose? Obviously, the slow soaker hose is better for the garden. Same thing with your furnace. I can either blast all the heat in your face, 120 degrees, and then shut it all off, or I can let it trickle out at 100, 105, 110 and heat your house more slowly but evenly. So you got to kind of explain it to them like that. It's not going to use any more gas. In fact, it's probably going to use less gas. It's going to be the most efficient furnace you can have, but it's also going to improve the comfort. Right? So you're going to get longer heating cycles. In some cases, it may not shut off for the entire hour. So that's going to be better discharge air control, better comfort. You're going to have less drafts and do a better job of distributing the heat throughout the home. Just like the variable speed furnace does a better job of distributing the air throughout the home and balancing it out a little bit, the gas valve modulating is going to do something similar. It's It's not going to fix bad ductwork, but it's going to help a little bit if you got some of those bonus rooms above the garage. This furnace shuts off, the ductwork gets cold because it's bordering the attic or bordering the garage attic, and then you first turn the furnace on, and then that cold duct has to warm up again before it goes into the bonus room. Well, if the duct's always got heat in it and it's always warm, I don't have that differential, and hence I don't have to overcome it, and hence I can have more heat actually go into the bonus room. I'm going to be able to keep pretty tight set point control, generally within 1 or 2/10 of a degree. So a normal thermostat, if I ask it to provide me 72 degrees for heating, it probably is going, when I drop down to 71 degrees, it turns on the heat. It heats the space till it gets to 72. Then it shuts the heat back off. It lets it drift down to 71. Then it turns it back on. That's a pretty normal thermostat. In fact, some thermostats even go down 1.5 degrees. So it'll go down to 70.5, turn on the heat, shut it off at 72, repeat the cycle. So you're basically going up and down 1 degree or 1.5 degrees all the time. Well, this guy doesn't do that because he doesn't have to shut off the burner. He modulates. So his goal is to get you up to 72 degrees and then not have to shut off. He wants to start backing off the gas valve as he's getting closer and closer and closer to 72. Back off the gas valve so I don't have to shut off, so I can hover at 72 or 71.8 or something like that. It's kind of like cruise control in your car. So you're driving along, you got your cruise control set for whatever, let's say 72 miles an hour to make the comparison similar. You slam on the brakes because the truck cut you off. Your car slows down to like, 60 miles an hour. You hit the resume button. The car starts accelerating. It says, all right, you want 72 miles an hour? I'm only going 60. Dang, I'm going to need a lot of gas to get you there. So I'm going to have to pump this guy up. So it basically depresses the accelerator all the way down for you, zooms it all the way up, but doesn't just shoot to 72 and then say, oh crap, I overshot it. It goes, 62, 65, 68, 70, and then it starts backing off. 70.5, 71, and backs it off a little bit more, so it ends up right at 72 miles an hour. That's exactly how this furnace operates. It comes out of setback at 60 degrees. It says, man, you want 72, and I'm only 60 because that's what I was at for the nighttime you told me. I'm going to have to put a lot of gas in and get this thing up towards 72 really quick. And he'll put a lot of gas in, ramp it up to 70, 70.5, whatever. Then he'll start backing off the gas valve to kind of end up at 72 and keep the gas valve at a low fire hovering there for a long time. That's kind of what his goal is to stay on all the time, but at low fire. So I'm able to tolerate pretty tight temperature control that way. And then the sound level, there is some benefit to not operating at 100% capacity. I'm not saying that this is the quietest furnace in the world, although it actually technically is the quietest furnace in the world. It is rated that way. But a lot of the sound benefits of the furnace come from the fact that it almost never has to be at 100% fire. Yeah, when I first come out of setback, it might have to, but for the most part, I'm not going to be at 100% fire unless it's a -5 degree day outside. So the lower firing rate I have on gas, the slower my inducer motor is, and the slower my blower motor is. And the inducer motor and my blower motor are my two biggest noise issues in a given home. The inducer motor radiates sound outward of the cabinet, so if you got it in a closet off the living room, people are going to hear that inducer motor. The blower noise doesn't radiate out the side of the cabinet, it discharges down the duct. So that's where they're going to hear that particular noise. But if both of those are running at a slower speed, it's going to be less noise and hence less noise complaints. All right, let me check and see if there's any questions here, and then we're going to talk a little bit about some of the energy stuff. All right, I don't got any new questions in here yet. If you guys got questions, type them in that question chat box, and I'll do my best to try to address your questions. So there's a couple different ways we can compare the energy side of some of these furnaces. One of them is the online op cost calculator. There's both a Carrier and Bryant version of this guy, and the way you access it is through HVAC Partners, hvacpartners.com. If you don't already have a login for it, go to that website and click on the request login button and get set up with one. If you're a Carrier or Bryant dealer, you'll pretty much be approved by our admin folks fairly quickly. If you are not a dealer, then they're probably going to have to verify that you actually are at least a customer of ours of some sort. So it might take a little bit longer. But they should have you up and going in 48 hours. So if you go into Carrier Residential Marketing, click on Software Tools. One of those tools is called the Online Op Cost Calculator. There's both a Carrier and Bryant one. I did some examples of them already on here and did a screenshot of them, so it would take a little bit less time than going and doing it. Generally, it only takes 5 minutes to do it, so it's pretty quick. But I already put a couple examples on here. So here's one example here. I only did these as a heating system. I did not put any cooling on these particular examples because I wanted to see the electrical cost that's specifically associated with the fan and not also have that compressor electrical cost skewing my results. So in this case, I put 100,000 BTU load on here, zero cooling, so no cooling. This is a Chicago area zip code, Melrose Park. At the time I did this screenshot, it was $1 a therm for gas, 10 cents for electric. If you were doing this again today, I'd probably tell you to use about 80 cents a therm and probably 11 or 12 cents on the electric side, just because the cost of gas has gone down below 60 cents a therm past 2 years, but prior to that it was up above $1. So if you kind of average it out, I'd say use 80 cents. But nonetheless, this is just an example of comparing one versus the other, so the actual cost doesn't matter. So you pick the base system, and this could either be the furnace they own today, or if this is a new system that they're putting in, it could be the entry-level one they're thinking about putting in. In most cases, it's retrofit, and it's the one they have today. So I picked basically the least efficient furnace I could find in the list. There's also some generic ones you can pick, like a generic 90 or something like that. But I picked a 310JA, which is an 80% AFUE furnace with a very inefficient PSC blower motor. So 80% AFUE, it's basically costing this BTU house in this zip code with these utility rates, it's costing this guy $2,800 a year to run for total heating cost, gas and electric combined. If you want to break it down, it's $2,300 for the gas, and it's $470 for the electrical cost. Then we got three other choices that we put in here. One of them is a 355 CAV, which is last year's model of a 3-stage gas furnace with variable speed fan. I got a 986 TA, which is the current 2-stage Evolution furnace with a variable speed motor, and then a 987 MA, which is the modulating gas furnace with a variable speed motor. So they go 95, 96, 97% AFUE, a little bit better on each one of those. That gas cost basically goes from 1980 to 1950 to 1940. I'm saving very few dollars going from 95 to 97%. It's just a few bucks. It's pretty substantial going from 80% to 97. That's $2,300 to 19. That's basically $400 in savings for me right there on the gas side. Look at the fan side. It was costing me $470 to run the fan. With the modulating gas one, it's only $80. And if I pick one of the 2- and 3-stage units, it's $110. So here's a PSC motor at $470. And then variable speed ECMs at like $110. The modulating gas one's even less. It's not because it has a more efficient fan motor. It's because the fan motor spends many more hours at low firing or low speed because the gas valve was at low firing rate. The lower the gas valve firing rate, if you heard me say before, the less speed I have on both my inducer and my blower motor. So that corresponds to a little bit more savings. So overall, if you take out your 80% PSC furnace and put in the modulating gas furnace, I'm going to save, in this example, $800 for this dude's house. So $800 is pretty nice. It's not, an absolute no-brainer. But if I just put in the Evolution 2-stage unit, I'd save $750. It's really only saving me $50 more. So if your plan is to sell the modulating gas furnace based on energy savings, it's going to be a tough sell. Yeah, it saves a boatload more than whatever they own today, but they can get almost all that savings by getting a nice 2-stage furnace. Get very close. So the $50 extra is not worth it from the energy standpoint. So the reason that you're going to sell a modulating gas furnace is not going to be on energy. It's going to be based on the comfort factor. Energy just comes along for the ride. It's just a bonus that it happens to be the most efficient furnace we make. The real benefit is the comfort benefit. Let's see, we had a couple of questions pop up. So Jeff asks, what's the average dollar savings for a homeowner per year by choosing a modulating furnace? I think you must have typed that in before I just did this description. I think we kind of answered that. The other one is from Sean. Can you email the slides for sales use? Yes, we can definitely do that, Sean. Let me do it this way, though. At the very end here, my email will be on here. Send me an email asking me what you want, and I will send it to you. Otherwise, I'm in the middle of presenting this, so I can't take any notes or anything right now to kind of figure out what you guys all want later. So send me an email of what you want, and I'll send you the slides that you need. All right, so just to give you a couple more examples, that was on natural gas. If I look at a propane example, and we'll stick with the same models we just had. So same exact heating size, same zip code, same electric cost. And this one I switched it from natural gas to propane at $2 a gallon. I don't know if that's still the current price, but usually it kind of hovers between $1.80 and $2.30 a gallon. And a lot of it depends on whether you pre-purchase it at the beginning of the year or whether you're buying it as needed and those kind of things. But the point is that propane costs way more to operate than natural gas because natural gas is ridiculously cheap right now. So then the decisions become even nicer. So this guy's particular example was costing him $5,600 a year for gas and electric, and now we're going to save him $1,300 by putting in the modulating gas unit. But once again, I could have went up to two-stage unit and saved $1,240. He's only getting like $50-$60 more savings by going from two-stage to modulating gas. So once again, the benefit of the modulating gas is the comfort. I'm not saying it doesn't save energy. Obviously, it saves a lot of energy compared to what the guy owns now. It's just between the two best furnaces that we have, it only saves a little bit more energy. The comfort's the real benefit. I already showed you earlier that the Infinity furnace is the most efficient one on the market. It also happens to be the quietest one. Specifically, they give you a exact size here. The 59 MN7A060V17-14 is the quietest one available on the market. At the time I made this slide, it was back in the fall, so I don't know if somebody else came out with a quieter one than that or not. Generally speaking, it's quieter than all the other competitors, but I'm assuming some of the sizes, it's not the absolute quietest. But overall, this is a pretty quiet unit. And once again, much of that is because the inducer and blower motor can slow down as well. John Ashley typed in a very good question. Are the modulating furnaces, it says comparable with most thermostats. I think he means compatible with most thermostats. That's a good point. These furnaces need to operate with the Infinity and Evolution thermostats. If you put on a regular thermostat, which you can temporarily do, and I believe there's a jumper wire you got to cut to use a temporary regular thermostat like in an emergency situation, it kind of disables all of the modulation sequences. So you really have to have the Infinity or Evolution stat for the modulating gas furnace to work correctly. And that's because we don't want to just know if there's a call for heat like a regular thermostat does. We want to know how much heat the thermostat wants. So I need to know both the space temperature and the set point and figure out the difference between the two. So if the space temperature is 71 degrees and the set point is 72, I know that I need 1 degree of heat. And I can calculate how much BTUs to put in. And then as I run that for a couple minutes, I can see how much effect that's having on my space temperature, and I can then decide to bring in more or less gas. So I can continuously modulate that guy. So I need to know specifically the deviation from set point that my actual temperature is, and I need to know the rate of change of the actual temperature of the room. So it's basically a PID loop for you guys that do commercial stuff, proportional integral derivative, although we're probably not really using a derivative term, proportional integral, where the proportional says how far from set point are you, and the integral says, well, how fast are you getting to the set point? I need to know those two things in order to modulate the valve. So you really got to have the Infinity or Evolution thermostat to use it with these modulating gas furnaces. The same thing coincidentally is true if you do the modulating variable speed compressor heat pump. That guy needs to have an Infinity or Evolution stat on him as well. So there are some sound apps available. These are available for iOS devices, which would be iPhones, iPads, and I guess iTouches if you want to use your kid's iTouch to do this. The other thing is you can actually go to a website directly, www.bryfurnaces.com, and you can run it from the website if you don't want to use an app on your phone, or if you have an Android phone that obviously doesn't support an Apple app, you can run it from the website if you want to. And then the carrier one is cacfurnaces.com. If you want to download the apps, you have to download them from HVAC partners. They are not available in the App Store to anybody. They're only available through partners for dealers. Kind of the idea with these apps is that you can compare a Bryant or Carrier furnace of one type to a Bryant or Carrier furnace of another type. Or you can compare that furnace to the top-of-the-line furnaces from various competitors, Lennox, Trane, Goodman, etc. So basically what you do is you pick two furnaces. Say they're choosing between you and the Goodman furnace, for example. So you pick the Goodman model number they have, you pick the Carrier model number you have, and then you would play a sound clip of each one. You can play it in low fire, you can play it in high fire, or you can play it during its startup sequence for like that first minute or whatever. My sound hearing is not very good, and generally most of these furnaces sound pretty much the same to me on low fire, but the high fire makes a pretty big difference in sound, and this Carrier one is usually the quietest one on that sound app. I say usually because if you don't pick the 59MN7 and you pick one of the other stage furnaces, it won't be the quietest one necessarily. So I might be able to pick the top of the line Goodman, but the second tier Carrier and the not Goodman, that's probably a bad example. That one never beats it. Say the top of the line Lennox one, that's a pretty quiet furnace. And the second tier Carrier one and the Lennox one might be quieter. But if I pick the top of the line Lennox and the top of the line Carrier, the Carrier one's going to end up being the quietest. But you can see the decibel levels that these guys had measured, and you can also actually play the sound clips. And then if you want, you can go look on the lab tab here, and it explains to you how the test lab works. Basically, they got a sound reverb room. They have ductwork in there. They put a Carrier furnace in, connected it all up, ran it, recorded it with a microphone at X feet away from it, took that furnace out, put in the Lennox, run it, record it, took that one out, put in the Goodman, ran it, recorded it, the train, etc. And basically plopped each one of these furnaces into the exact same room with the exact same ductwork, with the exact same microphone in the exact same position, and recorded all these sound clips, and you can play them. My only caution is that you play the sound clip before you show it to a customer, because like I said, if you're not offering the absolute quietest furnace on that given day, some of the competitors' ones may sound better than that. Additionally, if the customer's not looking at a competitor's furnace, don't show them the app. Why do you want them even knowing there's a quiet Lennox or a quiet Train or a quiet whatever? Only do that when you're competing against someone. All right, let's see. We got another question that came in from John. Will the Carrier Infinity thermostat allow a hybrid system that is both heat pump and gas furnace? The answer to that, John, is yes. You can run a dual fuel system. We typically call it hybrid heat, but it's basically a dual fuel system, and we can optimize running either the gas or the electric heat pump depending on who's more efficient to run at a given time. If you saw on that, well, you can't really see on here right now because I don't have a heat pump example on here, but if I would have chose cooling and I picked one of them with a heat pump, the heat pump, based on the utility prices that I put in, it would have actually calculated the breakpoints for me. The software example calculates the thermal breakpoint and the economic breakpoint. The thermal breakpoint is the outside air temperature at which the heat pump at the given size that I chose cannot produce enough heat to meet the load of the house at that given outdoor air temperature. The economic breakpoint is, well, based on this electric and this gas cost, when does it become cheaper to run my gas furnace? What outdoor air temperature? So the example might come up and say, oh, at, I don't know, I'll make one up. At 32 degrees and below, I can't generate enough heat for you with the heat pump by itself. But at 34 degrees, it's economically better to run the gas furnace anyway. So at that point, I would make my changeover point be 34 degrees. Below 34, run gas. Above 34, run heat pump. However, if my example was 32 for thermal breakpoint, but 28 for economics, then I would make my cutoff point be 32, because below 32, I can't get enough BTUs. So it can support dual fuel for gas furnace and electric heat pump, and obviously can also support electric heat pump with electric resistance heating as a backup as well. You can do either or. Anybody else have any questions they want to type in? And if you guys want me to send you any of these slides or anything like that, or a link to the recorded version of this presentation, that's my email address there. So you can just send me a note, and I will reply back to you either this evening or in the morning, depending when you send it, with whatever it is you asked for. Let me see if we have any more questions. Looks like we don't have any more questions at this time. So that's going to conclude our webinar. If you guys have questions, either give me a call or send me an email, and I'll do my best to address them. I am teaching classes most days, so if it's not an urgent thing, send me an email, and I'll try to respond to you in the evening. For example, when I leave here, I'm going to go teach a class right now, and then I'm going to teach a webinar tonight. So full schedule, but I'll try to get back to you tonight or tomorrow morning. Thank you guys for your time, and we'll talk to you later.